America's nuclear navy was born from espionage. Peak moment and setup. The reactor alarm chirps once, sharp, clinical, and the control room freezes. We're a whisper behind a Soviet boat in the Norwegian Sea, 100 meters down, and every hand knows the rule: speak softly or surface loud. The watch officer's eyes flick to the panel, to the throttleman, to the captain. Seconds. One wrong move and the coolant pumps betray us with a howl. Silence means survival, and the safeguard that keeps it quiet. It traces back to seized German notebooks and borrowed minds, and the people who paid for those pages. To understand why this reactor stays calm, we go to 1945. Ruins, espionage trails, and shopping lists where treaties should have been. Ruins and shopping lists. The 1945 Scramble. Germany's collapse didn't end with surrender. It started a hunt. Allied units with names that sounded bureaucratic, ALSOS, T-Force, Scientific Objectives Units, fanned across a broken map. Their orders read like scavenger hunts with geopolitical consequences. Find the people, the papers, the prototypes. While headlines focused on rockets at Peenemünde, quieter teams walked docks and basements in Kiel, Eckernförde, and tiny seaside workshops where U-boats had learned to vanish. Not glamorous, but decisive. Acoustics ledgers, torpedo fuse logs, blade geometry sketches, and the Peroxide dreams of Hellmuth Walter's closed-cycle propulsion. The unspoken pressure was psychological. Grab the mines before the other side does, or spend a decade fearing what you failed to seize. The stakes. The Red Army was sweeping west, and custody mattered more than ideology. Whoever reached a lab first decided whether technology became an American advantage, a Soviet threat, or a bargaining chip. Custody didn't just mean machines. It meant people who knew which cupboard held the test gauges and which valve always stuck. Vaults were pried open, crates inventoried, maps annotated with grease pencil. One officer wrote urgent beside a stack of bound notebooks that looked like personal diaries. They weren't. They were running records of tank tests, cavitation thresholds, and pressure hull weld failures, written in cramped German script, smudged by damp bunker air. At the naval testing grounds near Eckernförde, a small team found a torpedo gallery with walls still chalk-marked from last week's trial. On a shelf, thin brass cylinders labeled with microsecond delays. On the table, a half-eaten ration biscuit and a clipboard. The lab director, thin, exhausted, knew exactly what those cylinders fixed: premature detonations that had humiliated enemy boats. He also knew his staff would be split by the morning if he didn't choose a flag to face. His calculation was raw survival, custody by strangers or consequences at home. When the Americans arrived with cigarettes and a translator, he signed a short contract on a ration-stained table. 1 month, technical assistance, access to files. It would stretch into years. Peenemünde still drew cameras, but Kiel's shipyard offices carried the quieter gold. Filing cabinets held blade rate analyses, propeller pitch experiments, and hand-drawn maps of harbor noise that read like weather charts for sound. A locked safe in a basement locker room yielded decoy logic, how to fake a boat's acoustic signature long enough to slip a hunter's ear. Another door opened to Peroxide plumbing diagrams from Walter's workshops, sparse, elegant, and terrifying. The boats they powered, type XVII, the test beds, promised 40 knots underwater and delivered hospital wards full of chemical burns. Incredible speed, but loud, dangerous, and dependent on a volatile propellant that hissed like a fuse. Meanwhile, in the south, ALSOS teams were gathering nuclear expertise that would feed the Manhattan Project's post-war phases. But a subset of officers, naval minds, not air-minded rocketeers, kept asking unglamorous questions. What's the endurance profile of a submerged U-boat when it stops caring about air? How fast does noise grow when a pump cavitates? Where exactly does a hull sing when a blade tip kisses the wrong vapor bubble? They boxed not just devices but methods, test fixtures, calibration charts, and crucially, the culture of measurement that told engineers when to distrust the number on the gauge and the ego behind it. Custody disputes made for tense scenes. A Soviet major stepped into a lab just as a British T-Force party finished tagging crates. The British had paper, the Soviets had tanks, and the Americans had the trucks already loaded. There were handshakes, a promise to share, and then the convoy rolled anyway. In other towns, the inverse played out. The practical truth, both sides left with copies of things that didn't come in pairs. Blueprints could be photographed, notebooks transcribed. Human memory got conscripted, too. Technicians, invited to travel, found themselves at airfields with overnight bags and one-way itineraries. Some programs were already shattered. Walter's project sprawled across workshops and test stands. The Allies collected it in pieces. A peroxide pump without its pressure curve is scrap. But a pressure curve without the pump tells you how a new pump must behave. Fragmented German programs became roadmaps. Each missing piece pointed to a question American and British labs would try to answer. The immediate impact wasn't hardware rolling out of US yards. It was a framework of problems, ranked and notated. Quiet power over burst speed, endurance over sprint, depth without bubbles. Micro-stories like the contract on the ration-stained table repeated across the peninsula. A draftsman at Kiel carried out a wrapped parcel like a loaf of bread. Inside, a set of propeller templates with odd, scimitar edges. He explained the rationale with a pencil on the back of a requisition form: shift the blade rate peaks, push the vortices off the hull. An American lieutenant nodded, copied the drawing twice, and filed it under propulsor, experimental, examine with acoustic curves. Years later, a version of that scimitar would spin on a boat nobody could hear until it was already gone. Back in Washington, procurement memos piled up next to after-action reports that still smelled of damp paper. The sea services had to decide what to chase. Rockets were flashy, budgets tight, and diesel-electric submarines had just terrorized the Atlantic. Plenty of officers said good enough, but one name kept appearing in marginal notes, scribbled in a cramped hand. He wasn't asking for rockets. He was circling a possibility buried in those notebooks and test curves. Power with no air and no bubbles, power you could hide. While committees debated trophies, he chased a reactor, and the psychological edge of vanishing at will, the kind of invisibility that keeps enemy planners up at night. The quiet zealot, Rickover's early obsession. He arrived at Oak Ridge with a chip on his shoulder and left with a mission. Hyman Rickover looked at wartime labs and saw sloppy schedules wearing clean coats, vague milestones, optimistic charts, and a culture that forgave missed dates because the science is hard. He didn't buy it. At Oak Ridge, he learned nuclear from the pipes up, valves, shielding, heat exchangers, the way a pressure gauge lies if you don't bleed it. He also learned that complex systems only behave when people do, and people behave when process rules them, and when fear of failure is harnessed into discipline. Back in Navy circles, the mood didn't match his urgency. Diesel electrics had just carried the Atlantic War. The Type XXI's batteries and streamlining hinted at a new undersea era, but to many, nuclear sounded like a Jules Verne diversion. Let the Air Force chase atoms. Subs worked. Crews understood them. Fix torpedoes, refine sonar, tweak hulls. The argument was practical and cheap, and it missed the one figure buried in those German notebooks: endurance. German closed-cycle trials and Walter's peroxide logs proved that undersea warfare wasn't about bursts of speed. It was about staying down longer than the hunter's patience. Rickover devoured captured endurance data and the grim Walter lessons. Incredible submerged speed meant nothing if every sprint announced you across an ocean. The German curves told a more useful story. The moment a pump cavitates, the hull sings. The longer you avoid air, the safer you are. He reframed the problem. Speed was theater. Survival was endurance. And endurance required power with no snorkel, no oxygen trail, and minimal moving parts. That pointed past peroxide and into Neutron math. Reactors sized for boats, not cities, and crews trained to choose calm over glory. He wasn't a visionary in the romantic sense. He was a bureaucratic brawler. He clawed for billets that touched both the Atomic Energy Commission and Navy Materiel, a foot in each building so nobody could box him out. He wrote memos that read like indictments. Who's responsible? When will it be welded? Who signs the test card? When a committee said study, he said prototype. When an admiral said wait, he asked for the signature declining responsibility for delays. People started signing faster. Meanwhile, he kept a library in his head. German blade rate charts, pressure hull weld failures, closed-cycle autopsies, Oak Ridge heat transfer tables. He stitched them together into a doctrine. The plant isn't just power, it's a noise source. Therefore, the quietest plant wins. That meant design choices others saw as cautious. Go pressurized water reactor because the physics behaves and the control is predictable. Give up some power density if it buys stability and silence. Trade raw megawatts for pumps you can tame and loops you can isolate. He pushed for access to test stands and insisted on manufacturing discipline before blueprints set. If a valve seat wasn't concentric at the vendor, he wanted the purchase order revoked. If a welder's certification lapsed, halt the line. He created enemies. He also created a sense that nuclear propulsion would live or die on the dull parts, procurement, inspection, training, long before it met the sea. Process, not genius, would be the weapon. Navy skepticism didn't vanish. He met it with demonstrations and paper trails. He briefed endurance in hours, not slogans, and walked hostile rooms through failure modes. A pump trip that doesn't start a cascade because the human and the machine expect it. Shielding that protects without bloating displacement, maintenance intervals you can predict. He argued that a submarine built around a reactor isn't just faster, it's absent. Absent from periscope depth, absent from snorkel wakes, absent from the enemy's planning. Here's where the German Hall mattered for him. He pointed to their endurance experiments and their failures as proof that appetite without discipline kills sailors. Closed cycle promised speed and delivered burn units. Sloppy QA gave away boats through noise. The lesson wasn't copy Germany. It was copy their testing culture, then put a leash on it. He latched onto any captured alloy data, weld procedure, or heat transfer insight that made reactors quieter and safer, not just hotter. He kept moving up through relentless persistence, but he never relaxed the grip. He drafted requirements that read like threats. Document everything, test until boredom, then test again. He hired officers who could manage a drawing change and fire a chief for a sloppy log. He interviewed sailors like an interrogator, looking for the ones who would call a shutdown on a hunch and defend it. He told them the truth. Nobody will applaud you for a quiet plant, but a single noise you cause could start a war and put your crew's lives and your country's credibility on the line. While he fought paper, America imported people. Operation Paperclip was gathering naval minds, propulsor theorists, torpedo men, metallurgists, and they'd soon collide with his standards. He was ready. He didn't want celebrity scientists. He wanted their tables, tolerances, and mistakes bound into a process that would hold at sea. Operation Paperclip at sea level. Paperclip didn't just chase rocket men in lab coats. It sent quiet recruiters to shipyards and ordnance bunkers. Naval architects with oil under their fingernails, metallurgists who spoke in grain structures, acousticians who could read a wake by ear. Those were the targets. Files thick with torpedo trial data and propeller sketches mattered as much as V2 trajectories. The brief was simple. If it touches endurance, silence, or reliability under pressure, bring it home and keep the names off the press. Hellmuth Walter's teams were high on the list. Not for Peroxide itself. Everyone could see how volatile it was, but for their closed-cycle logic, their plumbing discipline, and the machining tolerances they'd forced into small hulls. Eckernford's torpedo specialists knew fuse timing to the microsecond and how to shape a nose to dodge early cavitation. Hydrodynamics minds from naval test tanks carried an intuition for blade shapes that moved noise away from hull resonances. That mix, propulsion, ordnance, flow, was the bloodstream of a future submarine program. The moral fog settled thick. Dossiers noted party membership, factory foremen with camp ties, and research grants from ministries everyone wanted to forget. Cold War urgency cut through it. Sanitized summaries replaced raw biographies. A box was checked. No significant political involvement. Another box. Critical technical knowledge. Visas followed. Some men brought families. Others traveled alone. Their history folded into a manila folder marked confidential and a promise of housing near American water. Labs and yards took them in quietly. In Connecticut, a propulsor group cleared a bench for a German engineer who'd spent the war sketching blade tips that looked wrong to the eye and right to the instrument. In Virginia, a torpedo range paired an Eckernford veteran with a young US lieutenant whose last sea tour had been spent cursing dud exploders. In California, welders learned why a bead that looked perfect could still sing under stress, and how preheat and post-weld heat treatment tamed microcracks before the ocean found them. The infusion was immediate, if not flashy. Cavitation math tightened. Instead of rules of thumb, designers got curves that predicted bubble inception at specific radii, loads, and speeds. Propeller theory grew new branches, skewed blades, variable pitch distributions, trailing-edge treatments that didn't just move water, but moved noise. Guidance logic tips trickled out of torpedo notebooks, subtle course corrections to keep a seeker from chasing its own wake, delay lines that made magnetic influence less gullible to the Earth's twitch. Welding know-how slipped into standards, rod choices, purge techniques, the patience required to avoid porosity in places a reactor loop could never forgive. Paperclip wasn't hero worship. Rickover's rising machine made sure of it. The imported experts sat in design reviews where the question was never, what did you do in 1943? It was, show us the test card. What were the boundary conditions? Where did it fail? The ones who thrived respected that rhythm. They sketched, then proved. They argued, then welded samples and cut them open. Those who wanted status without scrutiny fell away. Peroxide dreams faded without disappearing. The idea behind them, a dense energy source that didn't breathe and didn't bubble, stayed on the table, stripped of its chemical hazard. Meanwhile, Neutron math rose. Oak Ridge spreadsheets met Westinghouse Betty's drawings, and the conversation shifted. If we can move heat quietly, we can turn quiet into endurance. German inputs chimed in at the edges. Heat transfer coefficients at velocities relevant to small diameter tubing, alloy behavior under cyclic stress close to cavitation thresholds, seal designs that bled just enough to avoid chatter and panic. A micro scene played out at a propulsor review in Groton. An older engineer, recently arrived from the Baltic coast, penciled a blade planform that curled at the tip like a scythe. The US lead frowned. It looked inefficient. The German tapped a table of blade rate harmonics and pointed at a narrow trough between hull modes. Here. The American ran a quick calculation, then a tank test. The microphone told the story. A tone disappeared. Not everywhere, not magic. Just one predator's ear going blind at a range band that mattered. Ordnance saw similar moments. A fuse team confronted their own wartime shame, premature detonations and misses, by digging into captured timing stacks. They didn't copy, they diagnosed. Why did the German delay train ride out transients better? How did their contact horns avoid false positives at certain angles? Answers turned into new US tolerances, new acceptance tests, a culture that treated microseconds as life or death because, at depth, they are. Acoustics shops built libraries from the stolen ones. Flow noise curves, wake spectra, the counterintuitive fact that sometimes adding structure, rafts, damping, mass, made machines quieter because isolation trumped elegance. Machinery went onto rafts. Pumps got new impeller profiles with German fingerprints and American metallurgy. Gearboxes learned to whisper or got banished entirely. People noticed culture shifts. A machinist in Newport News found a German metallurgist standing over his shoulder not to criticize but to measure. Again, the visitor said, after a pass on a lathe. Slower, listen. The cut changed pitch. The surface finish crossed an invisible threshold that wouldn't matter on a truck axle but meant the world on a reactor pump shaft. That day wrote itself into a shop manual. The stakes sat behind every engineering win. Moral compromise brought technical advantage. Veterans in the hallway recognized accents and said nothing. A few asked hard questions and got careful answers or none at all. The program moved forward anyway, convinced that discipline would launder origin. Process would turn suspect knowledge into safe machines. By the time peroxide had been shelved as a propellant and kept as a cautionary tale, reactors were climbing the priority list. The logic was ruthless. Dense energy, no bubbles, controllable heat. But the path wasn't just physics. It was welders retrained, tolerances tightened, fuse logic refined, and propellers bent into shapes that looked strange and sounded like nothing at all. From peroxide dreams to neutron math, propulsion pivots. Walter boats promised a future that looked fast and died young. The trials were intoxicating, underwater speeds that made destroyer captains swear their stopwatches were broken. But every demonstration carried the same catch: the hiss and temper of high-test peroxide, plumbing that punished mistakes with white fire, and a noise signature that betrayed the sprint before it finished. The Germans had proven a point, just not the one they wanted. You could buy speed with risk and racket. It wouldn't keep you alive, under a hunter's ear. The takeaway, buried in those captured notebooks and reinforced by Allied post-war tank tests, was brutal in its simplicity. Dense energy without bubbles mattered more than speed, and silence mattered most. Peroxide gave density but punished silence. Batteries gave silence but starved endurance. The math pointed to a third path that had seemed science fiction in 1944 and looked inevitable by 1948. Reactors that traded flame and bubbles for neutrons and heat, then turned heat into motion quietly enough to hide the boat that carried it, and unnerve every escort commander who couldn't find what he knew was there. That's where Oak Ridge's reactor men met Westinghouse's Betty's engineers, and the conversation narrowed from nuclear power to a specific machine a sailor could trust. Pressurized water reactors weren't glamorous. They were conservative on purpose. Water as coolant and moderator, pressure to keep it liquid, loops you could isolate, a steam plant you already understood if you'd ever stood throttle watch. The question wasn't if it could make power, it was whether it could make power without yelling about it. Stakes stacked up around three hard constraints. Metallurgy limited temperatures and stresses. Alloys had to take neutron embrittlement, thermal cycling, and marine corrosion without turning brittle or singing at resonance. Pump noise threatened to turn a reactor into a drum kit. Impellers, bearings, and seals had to move tons of water through tight channels while whispering. Shielding mass pressed on displacement. Protect the crew from dose without turning the boat into a bulging target that couldn't turn or dive like a hunter. The action shifted from whiteboard to hardware. Betty's and Oak Ridge built test loops that punished metal and learned its language. German data on stainless compositions and weld metallurgy under vibratory stress slipped into American standards. Heat transfer tables that once lived in U-boat notebooks got recalculated for small diameter tubing at reactor loop velocities. Seal designs took on a new purpose: avoid chatter that created cavitation, because cavitation wasn't just efficiency lost, it was noise born. Designers faced the pump first. Traditional naval pumps were rugged and loud. Reactor coolant pumps needed to be civil. Engineers reshaped impellers, widened flow passages, refined clearances, and chose bearings that traded a fraction of efficiency for a slab of quiet. They learned to accept a heavier casing if it damped a blade-passing tone. What nobody knew at the time was how often those decisions, measured in decibels and grams, would be the difference between getting a contact and becoming one. Shielding forced difficult trades. You could stack lead, water, and steel until dose rates dropped into comfort, but every ton had to be justified against endurance and maneuverability. The solution wasn't one miracle material. It was geometry, placement, and ruthlessness about leakage paths. Rickover's fingerprints are in the paperwork. If it hums, isolate it. If it leaks, fix the cause. If it can fail, design so the failure mode is quiet. Tanks filled with borated water sat, where they also served as trim or reserve, doing double duty, so mass earned its keep. Meanwhile, the steam side learned humility. Loud, efficient turbines weren't the goal. Controllable, smooth turbines were. Gearboxes that sang got redesigned or cushioned. Even valve actuators faced suspicion. Every thunk that telegraphed through hull frames was an invitation. The reactor might be safe, but if the plant couldn't move heat without talking about it, the submarine wasn't a weapon, it was a rumor. The doctrine solidified. Submarine-first reactor logic. That meant rejecting raw megawatts in favor of quality megawatts. Heat you could move in fine increments. Pumps that wouldn't shout when throttled, control rods that would step with grace instead of lurching. Engineers built in natural circulation paths so the plant could move heat with no pump at lower powers, erasing a tone the ocean would have otherwise heard. They accepted complexity where it brought quiet, then crushed that complexity with procedures so simple a tired sailor could execute them at 30. Before anyone cut steel for a hull, the program made a decision that sounded slow and proved decisive. Build a landlocked ship. Prove every claim under controlled abuse. If a weld cracked, learn why in Idaho, not in the Norwegian Sea. If a pump tone crept into the wrong band, reshape the blade there, not after a commissioning ceremony. The Peroxide era had chased demonstrations. The Neutron era would grind through tests until silence became a property, not a hope, and fear became just another variable to control. Everything was about to hinge on that grind. S1W, the landlocked submarine plant. Idaho wasn't the ocean, but the fence line at the desert site felt like a shoreline. Inside it, the S1W prototype rose like a submarine sliced open and planted in dirt. Reactor, steam plant, turbines, reduction gears, piping runs, all of it full scale, all of it wired to consoles where sailors learned to think in heat and silence.